Okay, hi everybody. In this screencast, I want to continue with our conversation about integration by parts and some special circumstances continued. Okay, so what I want you to look at is right here. Just look at this for me right here. Okay, here's the original integral, and if we use the look in a toilet every day hint, we know that this is the choice for u, this is the choice for dv. Okay, and we make our du and d and v, and then we substitute right here. Okay, and what I want you to do here is take a second and notice that while this integrand here is not ideal, it is arguably simpler because look where I went. I went from a cubic times cos x to a quadratic times sine x. Okay. And then let's see, if I look at this integral here, this then requires parts again. So look down here in my green now, okay? When you use parts again, here's your choice of u and here is dv. And when I find du and v, I get now this. Okay, now notice here, I try to color code. This here is from here. And then here's minus the, and then in green right here, this is the second parts, okay? And then we have a situation again. So if you look at this, again, while it's not ideal, it is simpler because now we've gone from a cubic times sine x or cos x to a quadratic times sine x to cos x, and then to a linear times sine x and cos x. And, if we use parts again right here, this is my choice of u. And then finally, I get to, if you have to watch all your negatives and distribute the negatives and so on and so forth, here's what we're left with. Finally. And I say finally because now we have an integral that I can just integrate without having to use parts. And here is my final answer. Okay? So I want to, you don't have to necessarily write this whole thing out unless you want to. Because what I want to show you here is in certain kinds of integrals that have certain characteristics, there is a shortcut to doing parts repeatedly. Because if you look here, we had to use parts once, right? This is parts once right here, parts a second time, and then finally parts a third time. So there's a hint sometimes, and it works only in certain situations. There's a shortcut to getting straight to the answer here when you have repeated parts. Okay, what is that shortcut? All right, let's start over. So notice in the original integral, you have x cubed, which is differentiable to 0. This phrase means that if I keep taking derivatives repeatedly, so x cubed to 3x squared to 6x to 6 to 0, eventually I will hit 0. Okay, not all functions differentiate repeatedly to 0, right? So e to the x, for example, is not differentiable to 0. Sine x is not differentiable to 0, okay? So we have an entity here that is differentiable to 0. And in the look in a toilet every day, you will notice that most of the time, but not always. Actually, is it always? It might be always, everyone. Yeah, it is always. Oh, I got to think about that. Okay, well, for right now, most of the time, I'm going to say, I'm not going to commit yet. Most of the time, the part that is differentiable to 0 is the a, or algebraic, okay? The other part of the integrand, cos x, I'm going to refer to as dv, that portion, cos x, is what I call indefinitely integrable, which means I could integrate cos x forever. It will never hit a stopping point. For that matter, here, cos x could be differentiated forever, right? So if you have an integral where a part of the integrand, and it's a factor, right? A factor, which is connected by multiplication, a factor of the integrand is differentiable to 0, and the rest of the integrand is indefinitely integrable. Look what you can do. Ready? We're going to go over here, write down that which is differentiable to 0, take that derivative successively until you hit 0. Okay? Next to that, I'm going to put in the right-hand column here that which is the rest of the integrand, which is indefinitely integrable. I am now going to integrate this many times. So this goes to sine x, this goes to negative cos x, this goes to negative sine x, and this goes to cos x. Okay, so again, when you have an integral where a portion or a factor of the integrand is differentiable to 0 and the rest of the integrand is indefinitely integrable, what we're going to do here is set up this table, if you will. Okay, and when you have this table, you're going to take that portion that's differentiable to 0 and do that, differentiate down to 0, integrate that portion of the integrand that is indefinitely integrable that many times until you reach this same horizontal with 0. And then you're going to do this. Watch. You're going to pick up a pen. And you're going to make diagonals. Positive. Negative. Positive. Negative. What those arrows mean is the following. Positive 1 times x cubed sine x equals positive x cubed sine x. Negative 1 times 3x squared times negative cos x equals positive 3x squared cos x. Again, because this negative 1 times this product is negative. Okay, now we're down here. Times positive 1 times 6x times negative sine x. That gives you negative 6x sine x. And then finally, negative 1 right here times 6 times cos x gives you negative 6 cos x. And if you want to look at something here, guess what this is? This is this. Okay, so that is a shortcut. It's a great shortcut to use. Okay, it's a shortcut that we use when you have those, right, whoops, I'm so sorry. Maybe I just made you all motion sick. So sorry. Okay, you can use this technique of setting up a table, differentiating to 0, and then integrating by 0. Oh, what did I forget? There should be a plus C here. So this equals this. This is called tabular integration. I am fine with you in your head calling it tabular integration. I like to add the two words tabular integration by parts, which is just a shortcut for doing parts repeatedly. Again, it doesn't work all the time. It works when you have an integral where a portion of it, a factor of it, is differentiable to 0, and then the other factor of the integrand, or the remaining factor of the integrand, is indefinitely integrable. Okay, and yes, it always goes positive, negative, positive, negative. It always alternates starting with positive. Okay, so that's one little helpful little special case to look out for that saves you some time. Bye-bye.